Okay, so the next topic on chapter 2, this is, screencast number 7. It's on energy. Energy is a fundamental component of all environmental systems. We'll look at defining it, looking at the quality of it, how it changes, and how it all relates to environmental science. So first, just a few words about its definition. Energy is defined as the ability to do work. When you think of the energy from the sun, it has the ability to change carbon dioxide and water into glucose and oxygen. So the energy from the sun has the ability to do work. Just a minor note here, energy has been measured in different types of units throughout the world. And we're going to look at 3 of them down here. The calorie, such as in the food calorie that you're probably familiar with. BTUs, or British thermal units, which for whatever reason is used to measure the amount of energy that a particular air conditioner might have. And then the one that we use most often in environmental science is the kilowatt hours. And you can tell from the word kilo in it, it's a metric number, and we're going to use that in the future when we do a future lab on energy use and reading your energy bill. Okay, so it can be measured in different units, and we're typically going to be looking at the kilowatt hour. Energy also comes in different forms, and that's what we'll look at next, and it can be of high or low quality, which we will also look at next. So, forms of energy are kinetic energy or potential energy. All energy falls into one of those 2 categories. Kinetic energy is the energy of motion. So wind blows, so that moves, it's kinetic energy. Water flows, such as in a river over a dam, so that's kinetic. Electricity flows, that's a flow of electrons across a wire. And light also flows because that begins with a flow of electrons and then it's converted. And if we were in a classroom and lecture, I would show you how temperature is the measure of kinetic energy of the atoms or molecules that are making up a substance. And I'd show you by having put a thermometer in a jar of dirt, let it equilibrate to room temperature, so let's say 22 degrees C, and then I would pass that jar of dirt around the room and have students shake it. When they get tired of shaking it, they pass it on to the next person to shake it for a while. And then we would periodically stop and look at the temperature. And you would see that the temperature continued to increase as the jar was shaken. And that's because when the jar is shaken, the atoms and molecules are moving along faster, and so temperature is a measure of their movement. Okay, next we have potential energy, also important in environmental science, and that is stored energy. It has a potential to be released and to do work, but right now it's stored. And chemical energy is one form, and that's energy that is stored in the bonds of a particular molecule. So, for example, glucose, which we've seen, the C6H12O6. In between each of those carbons is a bond, which we've represented sometimes by drawing out C-C-C, and we will also look at using a molecular model. When those bonds are broken in the process of respiration, energy is released. Another form of chemical energy that's important would be, for example, a battery. So in a battery, chemical energy is stored and can be released over time. Mechanical energy, we don't deal with a whole lot here in environmental science, but just to give you a quick background, a typical example of mechanical energy is a rubber band that you might be able to stretch tightly. And so that energy is stored in the stretching of the rubber band, the connection between the different molecules that are making up that rubber band. And it's potential energy because if you let go and the rubber band returns to normal, it's also shooting across the room and becoming partly motion, kinetic energy. And the last one that we deal with again is nuclear energy, in which instead of being stored in the bonds between different atoms, you have one particular atom and it has energy stored in its nucleus, in its bonds between the protons and the neutrons that are in that nucleus. And they might be broken apart through natural decay. So in natural radioactive decay, the protons and neutrons in a particular atom, such as uranium, break apart and form two new elements and also release energy. And that energy is very harmful to cellular material, in particular to DNA and RNA. And so that is why it's dangerous. And also when the same type of thing in a nuclear fission reactor, the nuclear energy within an atom is released. Okay, so let's look at the first law of thermodynamics. Energy is neither created nor destroyed. It just changes form. Does that sound familiar? Think about the first law of matter. Matter is neither created nor destroyed. So, let's see what that means. They give the example here of gasoline and a car. Gasoline is chemical energy, potential chemical energy, into long, long molecules of carbon bound together with other items such as hydrogen and oxygen and phosphorus and all kinds of things. So chemical energy in gasoline has a high potential energy. And when that gasoline is combusted in the engine of a car, we get several types of energy outputs. The first is called a useful energy output, and that's kinetic energy, which moves the car forward. And so therefore it's useful. These other two types of energy are referred to as waste energy, and that would be heat and sound. Heat occurs from the friction in the engine, the tires on the road, applying brakes, and just the regular burning of the gasoline. And it's not useful. It just makes the car engine warmer, and then the air surrounding it warmer. And sound energy is another type of energy, which is waste energy. And you'll hear the motor, you'll hear the tires on the road surface, etc. And those are both referred to as waste energy. So in terms of quality, the gasoline, with its potential chemical energy, would be considered high quality. It doesn't mean it's good. It means it has more of an ability to do work than these other types of energy. These waste energies would be of lower quality. All right, now we're going to look at the second law of thermodynamics. So let's look at the definition of the second law of thermodynamics. When energy is transformed, the quantity of energy remains the same, but its ability to do work, which is its quality, diminishes. So the quantity stays the same, but the quality is diminished. Let's go back a slide to see what that would have meant in the car example. So the total amount of energy that is contained within the gasoline, that same quantity is still present in the energy outputs. But though some of it remains useful energy, much of it is waste energy, and it's just not able to do much with it. And we'll look at some of those issues later. So the quantity remains the same on both sides of this car, but the quality or the ability to do work diminishes. Okay, so this becomes important in environmental science, particularly when we consider our energy resources, such as coal, natural gas, and so forth. So we're going to look here at loss of quality. Again, not loss of quantity. Starting here is a coal burning plant. And it has a certain amount of energy in the coal that's present in that plant that is then burned or combusted to create electricity. So when that quantity of energy is combusted, 65% of that is released as heat, which is a low quality waste energy. 35% is converted to electricity, which moves electrons along a wire. And so it has a 35% efficiency. Then when you move to the energy flowing through the power lines, depending on their distance, they have average losses of about 10%. So it doesn't lose quite as much going through the power lines. So 90% of that goes directly to the appliance or whatever you are operating. So then you multiply your original 35% by your 90%. And the efficiency of this last item, in this case an incandescent light bulb or an old-fashioned light bulb, is really important. You can see an incandescent light bulb, only of all of that energy that's reaching it as electricity, only 5% turns into or is transformed to light, and 95% is just given off as heat. Which is why if you've ever touched a regular old-fashioned incandescent bulb, it gets hot, very hot over time. So the overall efficiency of obtaining that amount of light from burning a certain amount of coal is 35% times 90% times 5%, which it comes out to 1.6% efficiency. So if you had, let's say, 100 units of energy here in the coal, by the time you get to light, you're down to 1.6 units of energy. So that's very small and very inefficient. So as we go through later chapters, we'll look at the different energy sources and which resource has the highest or has the lowest, lowest waste or highest production. And we'll also look at technologies and how they can be developed to be more efficient and therefore require a lot less resource use. Okay, quickly here in the last couple of things, another example of what I was talking about would be the energy efficiency of an old-fashioned fireplace versus a new wood-burning stove. These are very inefficient. I once stayed in a house from the 1800s that was still only heated by fireplaces, and they were those giant walk-in fireplaces. And it was at a ski resort place that a friend of mine's parents owned this house. The heat was terrible. It was very warm if you were right next to the fireplace, but it just gave out a little apron of heat, and if you moved beyond, let's say, 6 feet of the fireplace, it was freezing cold. And modern wood stoves, if you have one of those in your homes, that can really significantly heat a room up very well. Okay, last, connecting energy conversions to ecological processes. Energy flows into ecosystems, typically coming from the sun, which makes the wind and water move. So we have examples of waterfalls, we have an example of tundra. We have a deep ocean vent here, which is heating some water and allowing for more biological life. And we have some other energy flows, such as chemo. And that will be it for this section, and I'll move on to another screencast.